Thank you for the introduction. My name is Wan Li. I come from Beijing University of Technology. I have done a study with the Gao Lai from City-Sinai Medical Center. So I'm going to start with a question. When you're looking into this picture, for example, your favorite dinner, and can you remember when did you eat it, and where did you eat it, and who did you eat it with, and what did you eat? If you can answer all these questions, congratulations, your episodic memory is working well. So what is episodic memory? Episodic memory is a collection of past personal experience that occurred at a particular time and place. That's why episodic memory can be explicitly stated. And the term of episodic memory has been first proposed by Andrew Turing in 1972, described as the remember has mentally traveled back to his or her past. So, do we have this episodic memory since we were born? The answer is yes. The preliminary episodic memory does exist in the infants. The study have shown that the babies can recognize their mom's voice or face just hours or days after birth. Another study shows that the episodic memory has experienced a dramatic development in the first years of our life, and they reported that at 9 months of age, the babies can store and retrieve representations over delays of as many as 4 weeks, but they can do this up to 6 months when they are 10 months old. But at the end of another end of life spectrum, episodic memory is one of the earliest decline brain functions. For example, it's harder for elders to recall a person's name, even though they recognize this person and they are sure they know this person's name. So, based on these findings, indicate that episodic memory is as one of the unique brain functions that emerges very early and declines as one of the earliest. So it's important to characterize a brain basis for this episodic memory. Hippocampus has been identified as a key region for the episodic memory. So in this study, we want to characterize a potential brain basis for this episodic memory change. In this study, we tested the hypothesis that hippocampal functional connectivity actually underlines the episodic memory changes, and we also hypothesized that this hippocampal functional connectivity would also have a faster synchronization during the first year and a rapid decline in the aging. So we collected 5 groups of subjects. 3 of them are infants and 2 of them are adults. After standard pre-processing at first, we average all the voxels of bilateral hippocampus voxel signal as the hippocampal signal. We then Pearson correlated hippocampal signals with all the other cortical voxels, and finally, we use one sample t-test to find within group significant connections. And here, particularly, we designed a pooled FDR correction, which we put all the data together to find a consistent threshold so we can compare the brain networks across groups. And here are the results. In the neonates, we can see this hippocampal functional connectivity concentrates at the nearby hippocampal areas, and there are including parahippocampal gyrus and some subcortical structures. And in the 1-year-old, there is a global network has been fully developed, which making this connectivity covered distributed areas, including posterior cingulate cortex and medial frontal cortex and lateral temporal gyrus and angular gyrus. And in the 2 years old, and there's no much change, but in the young adults, we can see there is a dramatic specialization of the network, especially we can see the disappearing of the connectivity in the dorsal part of a network, including the dorsal, anterior, and the posterior cingulate cortex. Finally, in the aging adults, we can see the connectivity are very limited and almost undetectable at this threshold. So this hippocampal functional connectivity change across the lifespan can be characterized as the faster synchronization during the first year and the dramatic specialization after 2 years of age till adulthood, and finally the rapid decline in the aging, which parallel the observed episodic memory changes and that support our hypothesis. And then we want to quantitatively to show the pattern of this change, and we want to show this pattern is unique to hippocampus. We select 6 regions from both primary and high-order functions, including precentral gyrus and the postcentral gyrus, calcarine sulcus, and the middle frontal gyrus, anterior and posterior cingulate cortex. And first, we calculate the normalized amount, which is a number of voxel connected in each group normalized by the young group. And in this figure, we can see the hippocampus is denoted in the right curve. We can see the hippocampus shows as the fastest growth during the first year and the rapidest decline in the aging, and finally reaching the lowest point. And then we calculate the effective amount, which is the percentage of overlapping voxels between the map of each group and the map of young adults. Again, the hippocampus shows the fastest growth during the first year and the rapidest decline in the aging, and reaching the lowest point at the end. And finally, we calculate the effective pattern to measure the global change. It is a Pearson correlation between the map of each group and the map of young adults. We can see that hippocampus starts at the lowest point and then has the fastest growth during the first year, and then shows the second rapidest decline in the aging, and finally reaching the second lowest endpoint. So in conclusion, hippocampal functional connectivity has its unique and dynamic changes across the lifespan, which can be characterized as the faster synchronization during the first year and the rapidest decline in the aging. And the nonlinear and dramatic lifespan change of hippocampal functional connectivity is highly parallel with the episodic memory changes across the lifespan, supporting that hippocampal functional connectivity may be the brain basis for the episodic memory changes. And there are also some limitations in our study. We use the fully longitudinal data in the infants, and there are also, but we use the sectional, cross-sectional adult data. And for the infants, they were sleeping when scanned, but the adults were awake. And there are also a large age gap between the infants and the adults, which may harbor some nonlinear change. To address this, we are currently looking into our sample to extend our young sample from infant to 10 years old, so we can to fill this blank in the future. And finally, I would like to thank to CSC give me a chance to working with Dr. Gao's lab in Cedars-Sinai Medical Center, and thanks to this open data sets helped me finish this study. And last but not least, I was thankful to this merit abstract award, give me this opportunity to attend this conference. Thank you.